As we continue on with our unit on data and statistics, we're working our way towards doing probability problems. And in order to calculate probability, eventually we're going to have to be able to count possible outcomes. And so that leads us to using the fundamental counting principle and the concept of permutations. So as an example, if we're in the lunch line and it turns out that at lunch we have an option of 3 different types of meat on a sandwich and we can select from 2 sides, the question is how many different lunch combinations are possible. So you could go burger and fries, burger and chips. That would be 2 different possibilities. You could go ham sandwich with fries, or a ham sandwich with chips. That's 2 more possibilities. Or a turkey sandwich with fries, or a turkey sandwich with chips. So that's 2 more. So a total of 6 different lunch combinations. Now we can count those because there were really very few combinations, but if we had hundreds or thousands of possible combinations, we wouldn't want to count them all or write them all down. It turns out that there's math for that, something called the fundamental counting principle. And what the fundamental counting principle says is this: if one event can occur in m different ways, such as being able to select 3 meats for a sandwich, and another event can occur in n ways, that would be your 2 sides that you can choose from, then the number of ways that both events can occur is m times n. If we take 3 events, like adding in a choice of beverage, so one event can occur in m ways, a second event in n, and then a third event in p ways. Now the number of ways that all 3 events can occur, we'd multiply those together, m times n times p. So 3 meats and 2 side options and 3 beverages, 3 times 2 times 3 is 18. We'd have 18 different ways that we could select from a meat, a side, and a beverage for lunch. And the counting principle extends out for 4 events or more. So let's look at an example. One that you've probably done before, selecting a PIN number for an ATM card. Now your PIN has 4 digits. The question is, how many different PIN numbers that have 4 digits are possible? And so let's take a look at this from the standpoint of each digit individually. And we could actually write down a box for each of these. And so how many different digits could possibly be selected for that first position? I can select any digit from 0 to 9. For the second position, again, I can select any digit from 0 to 9. The third position, any digit from 0 to 9, and the same with the fourth. And so I have 10 ways to make a first selection, 10 ways to make a second selection, 10 ways to make a third selection, and 10 ways to make a fourth selection. So 10 times 10 times 10 times 10. 10 to the 4th power, that's 1,000. So there are 4 different, 1,000 possible 4-digit combinations that are possible for a PIN number. And you can extend that out to any other way that you're selecting a 4-digit number. Let's look at another example. Perhaps you live in a state where license plates contain 3 letters followed by 3 digits. So how many license plates are there that are possible if the letters and digits can be repeated? So same story. Let's go ahead and set up separate boxes for each of these possibilities. So we think to ourselves, how many letters can I select from for that first box? Well, there's 26 letters, right? And if they can be repeated, I can use any of those 26 again. And then for the third position, there's still 26. And now 3 digits. Well, 3 positions, any of them can be 0 through 9. So there's 10 possibilities for the first digit, 10 possibilities for the second digit, and 10 possibilities for the third digit. So we would now multiply this out. 26 times 26 times 26 times 10 times 10 times 10. And that would tell you that there's 17,576,000 different license plates that are possible if we use 3 letters followed by 3 digits. Let's think about that another way. What if we're not allowed to repeat any of the letters and we're not allowed to repeat any of the digits? Well, similar story. I can use any of the 26 letters for the first position on the license plate, but for the second position, one of those letters has already been taken and I cannot use it again. So now I only have 25 options there. And for the third option, 2 of the letters have been accounted for, so I have only 24. We're going to repeat that process with the digits. I'm not going to repeat any of the digits. So I have 10 possibilities for the first digit, but one of them has been taken. I can't repeat it, so I only have 9 possibilities for the second and 8 for the third. So now we multiply through. 26 times 25 times 24 times 10 times 9 times 8. And that brings me down to 1,123,200 license plates. Pretty large difference. And so ordering a set of numbers, a set of objects, is what's called a permutation of the objects. By the fundamental counting principle, there are 6 different permutations of 3 objects. So, for instance, the letters A, B, C can be arranged in any of these 6 ways. I can start with A and then follow with B, or start with A and follow with C. I can start with B and follow that with either A or C. Start with C and follow with A, then or B. And so mathematically, we use the exclamation point as a symbol to represent that expression 3 times 2 times 1. And that symbol, the exclamation point, which you find on your calculator, is called a factorial. And so we would read that symbol as 3 factorial. And so, as a general rule, the number of permutations of n distinct objects is n factorial. And it is written like this. N factorial equals n times n minus 1 times n minus 2, working all the way back down to 1. So 4 factorial, if I'm doing the permutation of 4 objects, how many different ways can I arrange 4 objects? 4 times 3 times 2 times 1, or 6 objects. 6 times 5 times 4 times 3 times 2 times 1. And again, you'll probably find a key on your calculator that will perform that calculation for you. So let's try a couple of examples. Let's say there's 8 runners in a race. They're going to run the 100-meter dash. So in how many different orders can the runners cross the finish line? And so we recognize that after the first runner crosses the finish line, the winner of the race, now there's 7 runners behind them. Any of those 7 can finish second. Now after that person crosses the finish line in second place, there's 6 runners that are still on the track. So 6 that can finish third. So 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you go to your calculator. If you wish, you can type out all of those numbers, or if you go to your scientific calculator, and you find the factorial sign, you can use the factorial that will give you the same result. So 8 factorial is 313,040. So there's more than 300,000 ways, distinct ways, that 8 runners can cross the finish line. What if we think about that a different way? So the top 3 runners, those are your podium runners. They get the medals. And so how many different ways can we select 3 of the runners to finish first through third? So let's think about this. The first position, there's 8 possible. Then after the first runners cross the finish line, there's 7 more still in the race. So any of those 7 could cross second. And then 6 possibilities for third. So now we can't go 8 factorial. We can't use the factorial symbol anymore. But we would just multiply 8 times 7 times 6 and find out that there's 336 different ways that we can arrange 3 of those runners out of the 8 to finish first, second, and third. And this actually turns out to be a pretty important idea. How many different ways can we pick a group of items out of a larger group and put them in an order? So in that podium question, we talked about an ordered group of 3 athletes out of a group of 8 athletes. And we say a permutation of 8 objects taken 3 at a time. And it's written in kind of a unique way. We use that subscript, the first number, the 8, the total group, and then the capital letter P for permutations, and then behind the P, the subscript 3, lets us know we're selecting 3. And so we just wrote that that was 8 times 7 times 6. If you think about what's going on, we took the 8 factorial, and then we also divided out the number of runners who were not trying to place in order. How many different ways can we arrange 5 runners out of a group of 8? So we end up with 8 factorial over 8 minus 3 factorial. If we were to multiply this out, divide it out, we would get that same answer, 336. So you actually can use this formula for a permutation of a certain number of objects taken one group at a time. So NPR equals n factorial over the quantity n minus r factorial. A couple of examples. Say you have 10 books that you want to display on a bookshelf. In how many different ways could you line up those books from left to right? So this is a straight factorial problem. To your calculator you go. And you would type in 10, and then find your factorial key, which might look something like x with an exclamation point behind it. So 10 factorial is 3,628,800. A related question, if we were to select 4 of those 10 books to put out on display, like a teacher in a classroom or a person who wanted to highlight some books they've been reading lately. And so that is the permutation of 10 items taken 4 at a time. So we would take 10 factorial in our numerator. The denominator, we go 10 minus 4, which is 6 factorial. So 10 factorial divided by 6 factorial. And that ends up that there's 5,040 ways that we could select 4 things out of a group of 10 and put them in a particular order. So that's the idea behind permutations. Let's make sure that you go ahead and kind of cement your learning by going to your note summary and writing down 3 things that you learned today, 2 things that you want to know more about, and 1 big question that you still have, and include your connections, sketches, random thoughts, any type of graphics that might help you understand more deeply what we've learned today.